Let's suppose that we have two events, E and F, in a sample space. We're going to say that these two events are independent if the probability of E given that F happened is the same as the probability of E. That means that the fact that we know that F has happened, it doesn't affect the probability of E. If we replace this probability with the probability of E intersection with F over the probability of F, then we get that two events are independent if the probability of the intersection, right, is equal to the probability of E times the probability of F. Then this is going to be our definition. Then E and F are independent if this is true. Let's consider an example. Let's suppose that our experiment is to take a card from a deck of cards, of 52 cards. Then this is going to be output 1, output 52. And let's consider the event E that the card selected is an ace. And let's say F, the event that the card selected, we select an spade. Then we can check that these two events are independent. Sometimes it's not so obvious, but then we can use the formula. Then what is the probability of E? The probability of E, how many aces we have? We have 4, then is 4 over 52, which is 1 over 13. How many spades we have? The probability of F would be 13 over 52, which is 1/4. But then the event E intersection with F, it means that we select the ace of spades. What is the probability of this? There is only one card that has that property, then it's 1 over 52. And then we can check that the probability of E times the probability of F, this is equal to the probability of the intersection. This is 1 over 13 times 1/4, and this is 1 over 52. Another example of independent events is the following. Let's consider omega, modeling the experiment that we are tossing a coin 2 times. And let's suppose that all 4 events are equally likely. Then this sample space is head, 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 tail, tail, head, and tail, tail. Then for this experiment, let's consider E, the event that we get a head for the first coin. And let's suppose that F is the event that we get a tail for the second coin. Then here E is the subset head, head, and head, tail, and F is the subset we get a tail for the second, then is head, tail, and tail, tail. Then the probability of E is 2 over 4. The probability of F is 2 over 4. And in this case, E intersection with F is just a head-tail, and the probability of the intersection is 1/4, and clearly this is just the probability of E, which is 1/2, times the probability of F, which is 1/2. That means that these two events are independent. Let's finish this video with this experiment. Let's suppose that we roll 2 dice. Then in this case, the sample space is 1, 1, 1, 2, 1, 6, 2, 1, 2, 2, 2, 6, and 6, 1, 6, 2, 6, 6. Then the number of elements in omega is 36, and let's suppose that we are dealing with 2 fair dice. Then all the events are equally likely. Let's consider the event E, that the sum of the dice is 6, and let's consider the event F, that the first die is a 4. Then let's see if these two events are independent. What is E? E is the event 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. And F is the event 4, 1, 4, 2, until 4, 6. That means that the probability of E is 1, 2, 3, 4, 5, 5/36. The probability of F is, there are 6 elements, 6/36, which is 1/6. And let's see the intersection. E intersection with F is the event 4, 2. Then the probability of the intersection is 1/36. Now, to see if the events are independent, we need to check this formula. Then the question is 1/36 equal to 5 times over 36, the probability of E, times the probability of F, times 1/6, and this is equal to 5/6 times 6 is 36, 18, 216. Then are these two numbers the same? The answer is no, they are different, and for that reason E and F are independent. Notice that the situation would have been different if I changed this 6 with a 7. What would be different? In this case, the E would be 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. And therefore, the probability of E would have been 1, 2, 3, 4, 5, 6. Then it will be 6/36. And the intersection would have been 4, 3, which has probability 1/36. And in this case, if we want to check if the two events are independent or not, then we will have to check if 1/36 is equal to 1/6, which is the probability of E, times the probability of F, which is 1/6, and this is 1/36. In this case, this equation is true, then if we consider these two events, we can say that E and F are independent.